In the same way that we didn't use just the raw Placido disk images, that we used the color-coded maps, we need to find some way to display the wavefront data, to go from the array of little tiny dots to something that is usable clinically. And there are two ways of doing this. One way is to say, let's pretend that we're looking once more at the dog star, Sirius, and we are looking up there and we ask, what is the question? What is the question? This is the question. What is the image on the retina of the patient the patient with a certain aberration? And this is similar in a sense to the question that we asked during optics. If someone has a correction that's a spherocylinder and is not wearing spectacles, where does the convolutive stem fall on the patient's retina? Focal line, oval. Here we're saying, let's say in an emmetropic patient or a corrected patient with an aberration, what is the image formed? And you can see that there are a variety that are shown on this one slide. You'll see later on that there are a large number of potential answers. Trefoil produces the image you see in number 1 and number 4, coma in number 2 and number 3. The other way to approach things is to match the wavefront pattern to a Zernike polynomial. And we're going to discuss what Zernike polynomials are. So this is examples of point spread functions. And not only do point spread functions vary by wavefront, but they also vary by diffraction induced by the size of a pupil. There's nothing quantitative that I want to show you on this slide. I just want you to see the effect that pupil size has. So the idea of Zernike polynomials is this: is that the wavefront, this aberrated front coming out of the patient's eye represents a sort of surface. And what we want to do is we want to find a polynomial that will produce a surface that is the closest fit to the aberrated wavefront. And the name of the polynomials that we're going to be using are called Zernike polynomials. And what we're interested in is the degree of the Zernike polynomial, and it's given as the subscript on the z, z sub 1, z sub 2, this sort of thing. And the Zernike polynomials have names to them too, clinical names that we're going to see. If you can picture describing where the wavefront is, whether the wavefront is pushed a little forward or pulled a little back. No, it's an absolutely perfect wavefront, a perfect planar wavefront, but we're describing kind of its location in space. We refer to that as piston, and it is a Zernike polynomial written with a subscript of 0. Not important clinically. Similarly, if we were to take the entire wavefront and just tilt it, it's a perfect, absolutely perfectly planar wavefront, but we're tilting it, then that is called tip or tilt, and that's written as z subscript 1. Again, not something that's relevant to us clinically. Now, when we get to third order Zernike polynomials, let me just go back one step, because I want to make things every bit as confusing as they really are. A first degree Zernike polynomial is written with a subscript of 0. So the subscript is always kind of n-1. So piston is a first degree Zernike polynomial. Tip tilt is a second degree Zernike polynomial. All of the stuff that we are interested in clinically are third-degree Zernike polynomials. So astigmatism is a third-degree Zernike polynomial, and the wavefront looks sort of saddle-shaped. Defocus, meaning myopia or hyperopia, is also a third-order Zernike polynomial, third order. Fourth-order Zernike polynomials also have got clinical terms, but they're not things for which we correct with spectacles. So trefoil is like astigmatism, but with 3 lobes rather than 2. And coma is something that we see clinically, but again, it's not something that we're going to correct for with spectacles. These are fourth-order Zernike polynomials. Fifth-order Zernike polynomials are sometimes given names, but they're of kind of less relevance clinically. It's just, you know, these are further ways that the wavefront can be distorted. And, you know, in the same way that we're not going to see a perfectly planar wavefront, we're not going to see a perfectly spherical wavefront or an astigmatic wavefront that's perfect in that sense either. We're also not going to see perfect trefoil. We're not going to see perfect fifth or sixth or nth order Zernike polynomials. What we're looking for with the Zernike polynomial is to try to just get the best fit. This is an example of a random Zernike in some sense. Every actual Zernike, every actual wavefront is going to have some degree of randomness in it too. This is just a table once more showing us the different Zernike polynomials and once more piston, tilt are things that are not of interest to us clinically. Defocus and astigmatism are, and then we have words coma, trefoil, secondary coma. Okay. And these are the comparable point spread functions for the different Zernike polynomials. And I show you this not so much to get a sense of what's going on quantitatively. These are things that are extremely quantitative, but they're not really quantitative in a clinical sense. Rather, this is data that we're gathering in terms of the shape of the patient's wavefront, because there may be some clinical circumstances in which we correct for the wavefront. You have to be very, very careful, by the way, when you look at correction of wavefront. There's a big difference between things that are described as wavefront correcting and wavefront guided. That's sort of out of the scope of this lecture, but you have to be very skeptical when you see devices or surgical treatment patterns that are described as wavefront guided. You really have to ask the manufacturer exactly what that means, because wavefront guided does not necessarily mean that it's going to correct the patient's wavefront aberrations. Okay, and again, these are simulations based on the human eye producing kind of pseudo point spread functions based upon a wavefront measure. Now, does this mean that we're gonna just throw in the towel on correcting wavefront? Maybe we're going to discard the idea of correcting wavefront. Maybe we're going to do it with a laser. Certainly, the one reason that we can't do it with spectacles is that even if you produce a spectacle lens that corrects for the wavefront, as soon as the patient glances somewhere other than primary gaze, the wavefront correction of the lens is no longer going to line up with the aberration of the patient's own eye. So this is not something that's correctable with spectacles. However, wavefront errors are not the domain exclusively of ophthalmologists, And one big area where wavefront is an issue is in telescopes. And I promise I'll circle back to something clinical here, but let's see how this sort of thing is dealt with telescopes, because this is going to ultimately have some interest to us clinically. So the idea is that there's a science object in the sky. You and I refer to the science object as stars. I mean, doesn't have to be just stars, right? It could be a comet or a nebula or a planet. There's turbulence in the atmosphere of the Earth, and we can get around this by, putting the Hubble Space Telescope up in space, although the irony is it turned out that there were some optical problems with that too, right? But if we're here on Earth and we're observing things on Earth and the stars twinkle, and of course the reason that they twinkle is because of turbulence in the atmosphere of the Earth. We want to compensate for this turbulent layer. Well, the first thing to do is to measure turbulence, is to measure the distortion, is to measure the aberration in the wavefront of the light coming towards Earth. And we can, of course, do that by producing an aberration going out of the Earth. And we can do that by shooting a laser beam out into space. We're going to call that a guide star. And we're going to measure the distortion of the laser beam, and then we can correct for it with the science object. Now, how do we correct for it? We can correct for it by putting little actuators underneath the mirror at the bottom of that telescope there to distort the mirror slightly in a fashion that compensates for the aberrations, the wavefront aberrations that are induced by the atmosphere. And of course, turbulence is not something that's fixed, it's something that's changing. And we flex the main mirror of the telescope in a dynamic fashion to compensate for this turbulence layer. This is an example of a very small mirror that flexes, and we call this this technique to compensate for aberrations in the wavefront, particularly for dynamic aberrations in the wavefront. We call this adaptive optics. And adaptive optics are employed in a very limited clinical sense in ophthalmology too. And this is just an example of an image of a retina on the left done with conventional lenses, and on the right, by employing adaptive optics, we can image down to individual retinal cells. We're looking down on the retina here as if it were some beautiful little sunflower. Adaptive optics are have a clinical role, but a very limited clinical role now. It's likely that we're going to see adaptive optics as a subject of interest in ophthalmology going forward. And we also employ wavefront in potentially doing wavefront-driven refractive treatments to patients' corneas, and who knows, maybe at some point in the future to intraocular lenses too. Okay, thank you very much. I know that this was more of a course in refractive mapping than a lecture. I hope you have enjoyed it, and I would be delighted to answer any questions that you have. You know, you can always reach me at jyoungmd@gmail.com. You can visit the As Seen From Here twice monthly podcast at asseenfromhere.com. There is an entire 20 lecture course on clinical optics, and in fact more than 20 lectures if you work with the app, at openophthalmology.com. And you can see other lectures that I've given, including the lecture on intraocular lens calculation after LASIK at my professional blog, jyoungmd.com or jyoungmd.org. But once more, you can reach me at jyoungmd@gmail.com. Thank you so much.